Okay, so if this morning's session was the moon from a distance, now we're getting to the moon from close up. People actually going there and plans for the future. And our first speaker this afternoon is Professor Ian Crawford from Birkbeck College, and he's going to talk about the Apollo program and its legacy.
Well, thank you very much. It's a great pleasure to be here. Thank you to Joe for the invitation. So I do come from Birkbeck College, where we have a small group working in lunar science. And my brief was to talk about Apollo and its legacy. So there have been a lot of missions to the moon, well, quite a lot of missions to the moon before Apollo. There have been a lot of missions since Apollo, but I still think it's true to say, even today, that most of our knowledge of the moon is derived from the Apollo program. We're still, 45 years later, mining the legacy of Apollo. And I'll tell you some of that, but my talk's mostly going to be on the scientific legacy of Apollo. But I just want to, there is, of course, many other legacies. There's a huge cultural legacy. And I just want to start with this image that many of you will be familiar with. This is the famous so-called Earthrise image taken by Apollo 8, which was the first Apollo to go to the vicinity of the moon, even though, of course, they didn't land. And so you have this for the first time, really, in human history. You can see the Earth from space, from a low Earth orbit, to some extent. But the Earth is still a very big planet if you're only a few hundred kilometres above it. So to really see the Earth as a planet, you have to be further away. And it's only the Apollo missions have taken people to a kind of interplanetary distance to look back and see the Earth hanging in space as the planet that it is. I think this perspective, there is a case to be made that the environmental movement, our understanding of spaceship Earth, or the very concept of spaceship Earth, in part derives from this perspective. And I'm naive enough to think there are still environmental and geopolitical benefits of having this perspective of looking at the Earth from outside. But anyway, much of what I'm going to talk about is the scientific legacy of Apollo. Insofar as this talk's got a write-up, it was written up a few years ago in the Royal Astronomical Society's magazine, Astronomy and Geophysics, should anyone be interested. And I've got a few hard copies here, but only a few if anyone wants to pick them up later. So I guess, just to whiz you through the architecture of Apollo. I'm sure most people are familiar with this, but it takes a big rocket to launch 3 people and all their kit to 11 kilometres per second, which they have to do, or they won't escape from the Earth at all. So it's the Saturn V, this is the launch of Apollo 17. It was the only Apollo mission launched at night, and it was, of course, the last one. So almost the biggest rocket ever built. It's truly, the then Soviet Union was developing a somewhat bigger rocket for its moon program, but that didn't work very well. And so certainly the biggest successful rocket ever built. And its whole purpose was to carry this from here upwards. This is the Apollo Command and Service Module with a little capsule with 3 people on it. And then buried in this part on the top of the Saturn V rocket, a housing for the lunar module, which was folded up, of course, with its legs folded, which had to be deployed later, which took 2 people down to the moon. Here's a picture. This is the Apollo 15 Command and Service Module in lunar orbit. And just draw your attention, so here's the capsule, obviously with only 1 person in it now, because the photograph's been taken by a lunar module, taking 2 of these in there. Just draw your attention to this. This is the Apollo Science Instrument Bay. So although I'm going to focus most on the science that was done on the surface of the moon, we shouldn't forget that the orbiting Command and Service Module was also carried a range of scientific instruments into orbit about the moon. Much of that, it's true to say, has been surpassed by later generations that Helga will probably talk about later, of remote sensing spacecraft that have been sent to the moon in the last 40 years. But still, we shouldn't forget that the orbital science was also done as part of Apollo, in addition to the surface science. So just to get you into the spirit of things, this shows the lunar module this is the Apollo 14 lunar module. You see it deployed on the surface, and then the lower it's a two-stage rocket vehicle, essentially. The only habitable part is the upper stage, with the 2 Apollo moonwalking astronauts had to live in and ultimately take off in. So the bottom stage of the lunar module acts as a kind of launch pad for this upper stage to take the lunar module back to rendezvous with the command and service module in orbit about the moon. This is the Apollo 11 command and service, the Apollo 11 lunar module coming back. You see it's coming back, so it's got Aldrin and Armstrong inside because it doesn't have its legs, right? The legs are left behind on the moon, and another nice picture of a crescent Earth in the background. Now, from a science point of view, certainly from a lunar geology point of view, it's quite important to distinguish between the first 3 successful Apollo missions and the last 3. So from Apollo 15 onwards, so 15, 16 and 17, Apollo itself was of course a big geopolitical program. It was conceived as a geopolitical project, it was paid for as a geopolitical project. But the geopolitical success obviously came once Armstrong and Aldrin and Collins got back safely, because the US had at that point demonstrated its superiority in space exploration. So the later Apollos then had to do something before the program was cancelled, and science became a more and more integral component of Apollo as the missions proceeded. And by the last 3, 15, 16 and 17, science was really driving Apollo. I mean, the vehicles haven't been paid for by science, they've kind of been given to the lunar science community to use. So the site selections were driven by science, the astronaut training was largely driven by science, the landing sites, the equipment, and including this. So the last 3 Apollos famously carried this moon buggy, the lunar roving vehicle, so electric powered vehicle. This is the first one deployed on the moon. This is the Apollo 15 lunar roving vehicle. This is a 4-kilometre high mountain. This is Mount Hadley in the background. And this is Jim Irwin, who's just tinkering with the vehicle before it goes off on its first extravehicular activity. So I'll just draw your attention to these, several things. You won't be able to see all of them, but first, the sample bags. These sample bags are very important from a planetary geology point of view, because these are the things that the rock samples were collected in and brought back to Earth. There's a rake here for raking through the regolith to pick up small stones and other tools you probably can't make out. But these vehicles, because they enabled the astronauts to travel further than they could walk, faster than they could walk, and to carry more kit and to bring more rocks back than they could possibly have managed on foot, really did greatly facilitate Apollo as an exercise in field geology. 6 successful Apollo missions. So these are the 6 successful landing sites. So Apollo 11 here in the Sea of Tranquility, Apollo 12, 13 obviously didn't land, 14 here, 15, 16, 17. And we heard quite a lot about the moon earlier, so you can see the Apollo 16 was the only Apollo to land completely within what to a lunar geologist is called the lunar highlands. All of the others are on mare surfaces, although 15 and 17 are close to, and deliberately chosen to be close to mare highland boundaries, because to increase the diversity of the geology likely to be sampled. I just want to make a point about this picture though. It's often been said, it was said by people who really ought to know better, like presidents of the United States from time to time, that we've been to the moon. We don't have to go back to the moon again because we've been there and done it in some sense. Now that might be true as a geopolitical project, but it's certainly not true as a scientific one. If you look at the distribution, right, we can draw a line around these 6 landing sites, and the moon has a surface area about the same as the surface area of Africa. In fact, 10% bigger. So think of Africa and the Arabian Peninsula together. That's the surface area of the moon. And so the question is, would you say you'd explored Africa if you'd parachuted in 6 teams, 2 people each with a tent, into 6 localities, and they were allowed to travel a few kilometres away from their tent for 3 days only, maximum, before they had to leave, right? We would not have explored Africa doing it that way, and similarly we haven't explored the moon. And then you can look at the geographical spread. All of these sites are in the middle of the near side. Nothing to the high latitudes, nothing to the out here to the western limb. It's true that the then Soviet Union had 3 very successful robotic sample return missions, Lunar 16 here, 20 and 24, out towards the eastern limb. But even if we include those, that makes 9 places on the moon from which samples have been returned. We still draw a sort of contour like this. It's all the middle of the near side, low latitudes, nothing from the high latitudes, nothing from the poles, nothing from the far side at all. So the moon, actually, yes, we've done a very good reconnaissance of the moon, but it's completely, that is to say, we've done quite a good reconnaissance of the middle of the near side of the moon. It certainly can't possibly claim to have explored the moon. It's quite interesting to go on to look at, of course, since Apollo, so 45 years since Apollo landed people on the moon, in the intervening decades, quite a number of spacecraft have been sent to the moon, studying it from orbit, and they include a very successful US spacecraft called Lunar Reconnaissance Orbiter, which is orbiting the moon even as I speak, which carries amongst its instrument packages the Lunar Reconnaissance Orbiter camera, which is one of the highest resolution imaging cameras flown to another planet. There's a comparably high resolution instrument orbiting Mars, but basically it's got a spatial resolution of about 50 centimetres on the lunar surface. So anything about the size of the chairs you're sitting on can now be resolved on the lunar surface from the orbiting camera on Lunar Reconnaissance Orbiter, which means, of course, all of these old landing sites can be resolved, and of course they've all been imaged. And if you go to the Lunar Reconnaissance Orbiter website, you can see all these images. So I just show this image of the Apollo 17 landing site as it is viewed today, or a couple of years ago, so 40 years after Apollo 17 landed, basically. This is what the site looks like today. I don't know how good the contrast is in this room, but this bright spot here, which blows up, if you blow it up so it pixelates, it's this funny shape. This is the Apollo 17 descent module. It's that part of the lunar module left on the ground to act as a launching pad for the ascent stage. And these are the rover tracks. You see, they're all this is 100 metre scale, right? So this is only the innermost part of the Apollo 17 landing site. But so for 100 metres or so around the landing site. These are the rover tracks. So still obviously completely pristine 40 years later, because it will take millions of years for the micrometeorite flux to significantly erode these tyre tracks. And then scattered around there's some equipment. Here's the lunar roving vehicle parked. The LSET packages I'll come to in a minute, but these are the main scientific instruments that were left behind, and they share as little white dots in these LROC images. So, starting with the scientific legacy of Apollo, and I'm going to start with geology, because the moon is a planet and geology is the study of planets. And indeed, this shows the first and so far only geologist to go to the moon. This is Harrison Schmitt, who got his PhD in geology from Harvard in 1964, and here he is on the moon in 1972. And these are blocky rims around a small, about 600, 700 metre impact crater called Camelot crater, local to the Apollo 17 landing site. And he's carrying he's carrying a spade here, or some other sampling tool. And Apollo really did, to my mind, demonstrate the efficiency, proved the efficiency of humans as field geologists on other planetary surfaces. It's a very strong case I'll come to at the end if I have time, for returning people to the moon. Ultimately, there's strong scientific reasons for sending people to Mars, I think, and perhaps elsewhere. And part of the scientific reason is the efficiency of human. I mean, it's expensive to send people to other planets, and it's dangerous. But once they're there, they are very efficient explorers. And I can try and justify that, perhaps a little bit, in even the next slide. This shows a sort of synoptic view of the Apollo 17 landing site. This is the Taurus-Littrow Valley. If I just go back to just remind you where it is sort of globally, it's here on the sort of the southeastern part of Mare Serenitatis. So it's the Sea of Serenity. And there's a valley here between the Mare basalt and the highland surroundings called the Taurus-Littrow Valley. And here it is imaged by the Apollo Command and Service module in orbit. So you've got the Mare Serenitatis is out here, sort of looking west here. These mountains, which have locally been called the North Massif, South Massif, West Massif, form part of the rim of the Serenitatis impact basin. And then the valley has been flooded with Mare basalt a long time ago. Of course, we know how long ago because we brought the rocks back. So the Mare basalt in this valley is 3.75 billion years old. So 3.75 thousand million years ago, this area of the moon became flooded with lava, which we now have 3,750 million years later, Apollo 17 landed here. And then I've drawn on the, this valley is 8 kilometres wide, and these white lines show the 3 traverses done by the Apollo 17 astronauts while they were on the moon. So the first traverse is only short because on the first EVA, each EVA could only last 8 hours because that's how long the oxygen and other sustainable things that they needed to keep them alive lasted for in the backpacks. But the first drive down to this little crater in the middle of this cluster of craters was relatively short because the astronauts during the first EVA had to spend a lot of time deploying a lot of equipment and actually drilling the deepest hole that's ever been dug on another planet yet. That's the Apollo 17 3-metre drill hole. Anyway, all of that took a lot of time. And then the next 2 days, they drove off to the South Massif and back, past some very interesting geology. I mean, this is, you can see this is the famous Apollo 17 orange soil, and it's basically a volcanic ash produced by a fire fountaining eruption here in the Taurus-Littrow Valley. Like you see, imagine these fire fountains you see in Hawaii that produce ash like this. It's a high titanium basalt, it's tinged orange. A long time ago. This is the youngest thing that's happened in this valley, this fire fountain that produced this volcanic ash, and that was 3.6 billion years ago. Some other interesting rocks I don't have time to talk about collected. But the point is, I just want to make 2 points. Firstly, this site was a geologically very diverse site, and it was chosen for that reason. And the second thing is that, equipped with a lunar roving vehicle, the astronauts very efficiently, in just 3 days, were able to cross from one side of this valley to the other, collecting a wide diversity of different rock types, deploying a wide variety of geophysical equipment, I'll come to that later, drilling a 3-metre borehole and returning the borehole to the Earth, and bringing back about, in this just Apollo 17 alone, about 76 kilograms of lunar soils and rocks for analysis. The other point I want to make, I mean, this may not look too impressive, 8 kilometres wide, but this valley was explored from one side to the other in 3 days by these astronauts. If you could just compare this with the rate at which exploration is progressing with Mars rovers, for example, the Curiosity rover, which is still active on Mars, which is fantastic because it was landed there in, not Curiosity, sorry, Opportunity, which landed in 2004, so it's been on Mars this little robot's been functioning for 12 years, which is fantastic. But it took Opportunity 9 years to travel the cumulative distance, which is 32 kilometres, that the Apollo astronauts did in 3 days. So this is part of my argument, which I'm not going to dwell on now, but I'll be happy to defend further during the questions. So why human exploration is so efficient. I mean, you compare 3 days of field work with 9 years with a little rover that hasn't drilled any boreholes, hasn't returned any rock samples, hasn't deployed any geophysical instruments. I mean, it has made some interesting in situ geological analyses, but compared to the huge scientific yield of the Apollo programs, it doesn't really bear comparison. Anyway, so first thing I'm going to talk about the rocks. Now, there are people in this room. There's Neil Bowles at the back, who's working on Apollo rocks in Oxford, and there's Mahesh here, who's working on Apollo rocks in Milton Keynes, and our group is working on Apollo rocks. This is some of our Apollo 12 soils. We're working on Apollo 12 soils in Birkbeck. So so 45 years later, we are still mining just the rock sample legacy. Right, and there are other legacies which I'll come to. Just the rock samples are still, studying the rock samples are still yielding valuable information about the geological history and evolution of the moon. And of course, instruments, the kind of instruments that we use to study rock samples are now much more sophisticated than they were 40 years ago. So NASA were very wise not to give out this total, 382 kilograms in total rocks and soils came back from the moon with Apollo. It's very wise not to just give that all out at once in 1972, because instrumentation now, we can get so much more out of these samples than would have been possible at the time. So I've got this summary. Now I'm sorry this may seem rather prosaic, all these boring scientific things that we're getting out of the moon rocks. But I think if I'm going to justify the scientific benefits of Apollo and later the scientific benefits of going back to the moon, I do have to show you that there is real science in these samples. So the first thing I want to, and I've got one slide to illustrate most of these each. Calibration of the inner solar system cratering rate. This is understanding the rate at which meteorites run into planetary bodies in the solar system. Studying the moon samples have told us a lot about the origin of the moon. In fact, our prevailing paradigm for the origin of the moon, the giant impact theory, only arose after Apollo, once those rocks started to be analysed. Of course, the moon is a very interesting geological object. It's a very interesting planetary body in its own right. It's a small one, of course, but that's interesting because it means being small, its own geology largely shut down a long time ago. So it's sitting there as essentially a small planetary body frozen in time, as it was shortly after it solidified. It gives us an insight into the earliest phases of planetary evolution that more complicated planets like the Earth and Mars have sort of recycled. It's become clear the lunar surface has acted as a big sponge that soaks up everything that falls on it from space. So meteorites, big and small, solar wind, galactic cosmic rays. And then calibration of orbital remote sensing instruments sounds pretty dull. But if you send remote sensing instruments to study other planets by orbiting spectrometers of various kinds, you have to be confident that you're interpreting these spectra correctly. And these instruments have to be can only be calibrated to confidence if you fly instruments over places where you've got some ground truth, where you've actually been and know what the compositions of the rocks are, because you've been there. And then if the orbiting remote sensing instruments give you the same answer, tell you a certain rock type, a certain mineral is in the place you know it to be, you'll have confidence in the instrument if it tells you that it's discovered some interesting rock type on the far side of the moon or the surface of Mars or somewhere else where we don't have samples from. So just quickly going through these. This shows a large crater on the far side of the moon. And what we learned from Apollo is that the rate at which craters formed on the moon, and so probably throughout the whole solar system, certainly the inner solar system, is there's a graph of number of craters versus time. And this is time in billions of years, so thousands of millions of years. And you can see before about 3.5 billion years ago, there were a lot of things, a lot of meteorites hitting the moon. It's declined very fast, and about 3.5 billion years ago, the impact rate has tailed off again. Now this seems not kind of thing that you might expect, and not too exciting, except that once you can only calibrate a curve like this if you can go to a planetary surface on which you can count the number of craters, say per square kilometre, and that's an easy thing to do. But you can only put an absolute timescale on this if someone or something has collected rocks from that area on which you've counted the craters and derived an absolute age. And the only place that has happened in the solar system, apart from the Earth obviously, is the moon. Without the Apollo samples, we would not be able to calibrate the rate at which craters have been formed on planetary surfaces. And this is important for multiple reasons. It means we can estimate the age, this is a picture of the far side, it means we can estimate the ages of surfaces on the far side from which we've not got any samples from, just by counting craters and going to this graph and reading off an age. But it also means, until we're in the happy position of having samples from Mars or from Mercury or other places in the solar system, the only handle that we've got for estimating the ages of planetary surfaces throughout the whole solar system through counting craters, the only way to tie those crater densities to reality is from the lunar calibrated impact cratering rate. So that's a huge, for planetary science, that's a huge Apollo legacy. If we think Olympus Mons had its last eruption 400 million years ago, that number has come just by counting craters on the flanks of Olympus Mons and applying the lunar cratering rate. Now, there's a whole lot of assumptions in there, right, which we can pick apart, but currently it's the best we can do. And until we get samples back from Olympus Mons, we won't be able to do any better. So in planetary science, just dating the rate at which craters form has been a huge legacy. Origin of the moon. So our current paradigm for the formation of the moon is that the early Earth got struck by a large object, probably a Mars-sized object, about 4.5 billion years ago, which vaporised or melted most of the impacting object and a good part of the Earth's mantle. and that the moon has accreted from a debris disk that orbited the early Earth. I mean, at first sight, this is quite an extravagant theory, right? You've got to ask, where did this giant impact come from and all the rest. But its real strength is that it explains the geochemistry of the moon to a reasonable degree of precision. I'm conscious that Mahesh is in the audience. I mean, it's not a done deal, this giant impact theory, but it is our current best paradigm because it explains why lunar materials are so relatively volatile and poor, and why the moon as a whole has such a small iron core. Basically the volatile bit is that if you vaporise part of the Earth's mantle and an impacting planetesimal, the volatiles will vaporise, which is an energetic event. Many of them will be swept up by the solar wind, ionised by solar ultraviolet, swept away. And what you've got left to condense a moon out of will be relatively volatile poor. This has only become our standard paradigm for the formation of the moon since Apollo, and it rests on the analysis of the lunar samples. Then I've already made this point about calibrating remote sensing data, but just to bring it home a little bit, this is an image of the titanium concentration on the surface of the moon mapped by the Clementine spacecraft. Now, Clementine was a US spacecraft that orbited the moon in the early 1990s, didn't land, it just took very coarse spectra, well really it was multispectral imaging, very low resolution spectra of the lunar surface, essentially just measuring half a dozen different colours, from which, but different minerals have different reflectivities at different wavelengths, and so from that it's been possible to, in this case, deduce the distribution of titanium on the lunar surface. Red means there's a lot, blue on the far side means there isn't any, or not much. And you can see the bit in red are some of, but not all, of the near-side Mare basalt are relatively titanium rich. So Sea of Tranquility here, this is titanium rich. But if you look at Serenitatis here and half of Imbrium, they're kind of missing because they're lavas, but they're not titanium rich. Anyway, we knew Sea of Tranquility lavas were titanium rich because Apollo 11 landed there and brought some back. But we didn't know that all these lavas over in the Western Hemisphere were titanium rich because no spacecraft has ever landed there. So we only know that thanks to the remote sensing data. But we only trust the remote sensing data because it's been calibrated from a point where we do have actual samples. Okay, so this is the scientific legacy of the moon rocks and the lunar samples. It's very important, though, that we don't forget other sciences which have benefited, other aspects of planetary science that have benefited from Apollo. So, in particular, we should remember the geophysics experiments that were performed during the Apollo missions. And there were several of these, but I'll start with the seismology ones. So all Apollo missions carried seismometers to the moon, although the Apollo 11 one was a bit different and short-lived, and the Apollo 17 was tuned to a particular particular type of experiment that I don't think I have time to talk about, which means that the main Apollo seismic network is sort of formed from the remaining Apollos, which I have this picture here, will help. Sort of a big equilateral triangle like this, about 1,100 kilometres on a side. Apollo 15 at the top, 12 and 14 close to each other at this corner, 16 there, right? So these seismometers were implanted by these Apollo missions, and they were left running until 1978, when they were switched off in a piece of scientific vandalism that no one could quite understand, because since they were powered by radioactive batteries, they could have lasted much longer. Anyway, this shows the Apollo 14 seismometer. The seismometer is here. It's surrounded by this silvery skirt arrangement to try and keep some sort of constant temperature around the thing as the sun goes up and down in the sky. This is its central data collection, powering unit. So this is one of the ALSET instruments that I've pointed out in the previous slide. Anyway, no new seismic data have come back from the moon since 1978, but just as with the rocks, since in the last 40 years, the tools that geophysicists use to get information out of seismic data have got much, much better. So you can still apply the old Apollo seismic data to and put them through new computer algorithms. And this has produced our current understanding of the inside of the moon with a small molten a small solid iron core, a small molten annulus around it. Just because it was mentioned earlier, these seismometers, of course, did discover several types of natural moonquake. And at least one of these, the so-called deep moonquakes, which have their epicenters down here near the core mantle boundary, these are tidally driven. These have a tidal periodicity in them, and they're due to flexure of the lunar interior due to tides raised in the moon by the Earth. There are also some very interesting shallow moonquakes whose origin is still unknown. And then moving on from the seismology, the moon is the only planet in the solar system apart from the Earth that has had its heat flow measured. This is David Scott from Apollo 15, lowering down into a 2-metre borehole which he has drilled a cable with some thermocouples on it to measure the temperature gradient in the uppermost few metres, from which you can derive the rate at which the moon is losing heat. And at least, so 2 of these were deployed for the 15 and 17 site, and the answer is similar in both cases. It's about 20 milliwatts per square metre. And this shows one of the laser reflectors. So one of the reasons we know the moon is moving away from us is because we're measuring it still now, 45 years after these laser reflectors were deployed. Laser beams are fired at them from telescopes on the Earth, and the light travel time from the Earth to the reflector and back is measured, which tells us that the moon is moving away at 3.7 centimetres per year. And it is per year, it's not per century, which was kind of mentioned earlier. Anyway, I just want to, sorry, this much per year. The moon is getting further away from us. Anyway, so I just, I see I've been waved at to say I've only got 5 minutes left. This shows Buzz Aldrin's boot. And this shows a close-up of the lunar regolith, which is the lunar soil, essentially. And I just want to make one claim, one case. We've learned there's a lot of stuff in this regolith, right? I've mentioned it: meteorites, solar wind, galactic cosmic rays. And Apollo told us this regolith has been soaking stuff up for billions of years. But I think there's a strong case for going back to the moon and collecting. We could go back to the moon in a more controlled way to sample lunar regoliths, and especially old regoliths, which haven't been exposed for billions of years, but were exposed for a little while and then covered up. And so this would be a paleoregolith, a buried soil. And then if you have a soil and it collects stuff falling on it from space, and then you cover it up with a younger lava flow, everything that regolith has soaked up while it was on the surface can then be assigned a particular time horizon. It's all come from the time between the regolith formed, which is will be the age of the underlying rock unit on which the regolith is developed. Stuff will fall on it, say solar wind from activity on the sun, or galactic cosmic rays, this is not the galaxy, of course, this is Messier 51, but it is a spiral galaxy, right? So if this were the galaxy, we've been sort of round it 20 times since the solar system formed, through all of these interesting places: spiral arms, supernovae, dense interstellar clouds. All of this stuff may have left imprints on the moon. The lunar regolith may have soaked this stuff up and preserved it. And I think going back to analyse this stuff will be not the only reason. I've got a list as long as my arm of reasons to go back to the moon. But one of the reasons for wanting to go back to the moon would be to study ancient regoliths to work out the evolution of the solar wind through time, and the location of the sun in the galaxy through. I mean, let me just go back, put this into perspective. I've only got 3 slides left. If this were our galaxy, right, what would you pay to build a Starship Enterprise or something that would go around the galaxy like this, collecting stuff as it went? And the thing is, the moon, the surface of the moon has been, well, all of the exposed surfaces in the solar system have been doing this, but the moon is the closest to this, and the moon has geological processes which have helped preserve these ancient soils with arguably ancient astronomical records embedded. We know they're there because if you look at this, is a collapse pit, which is probably a collapsed ceiling of a lava tube on the moon, and I don't have time to explain this diagram, but you get the idea. You see that the lava, this is Mare Angenae on the far side, but there are similar ones on the near side. The lava flows are layered, where the holes opened up, because surface has collapsed. This is interesting in itself. It implies there are voids below the surface of the moon, lava tubes or whatnot. But where the ceiling has collapsed, you see the lavas are bedded, and these lavas will all have different ages. I mean, you can imagine abseiling down here, collecting samples as you went, and you'd be sampling different parts of the moon's history, of course, but also different parts of the history of the space environment through which the Earth has passed. So abseiling down, sampling might be one way to go. Drilling might be another way to go, and I think drilling in search of paleoregoliths is one of, not the only, but one of the reasons I think why lunar science would benefit from humans returning to the moon, because it's kind of stuff on a scale that may be difficult to implement with small-scale robotic explorers. And this is my last slide, and it's going to lead on to what Helga's going to say, I think. I think, having said that, I think there are good reasons to go back to the moon. There are some positive signs in international space policy. It's difficult to predict the future, but there are several things happening. All the space agencies of the world did come together 2 years ago to make, 3 years ago, to make this thing, the Global Exploration Roadmap, which is an attempt to coordinate space exploration activities globally. And the human return to the moon fits in as an obvious stepping stone within the Global Exploration Roadmap before you were to aspire to send people further afield in the solar system. And then the current Director General of the European Space Agency, Jan Werner, has for several years now, and I know Helga's don't want to steal Helga's thunder because she's going to talk about it, but for some years now he's been advocating this moon village concept. And I think if you imagine a moon village grow up slowly, of course, but if you imagine it ultimately growing into something that was like an Antarctic-style research station, just as the research bases in Antarctica, like McMurdo or Concordia, they enable a huge amount of science to happen in the Antarctic continent, right? Geology, biology, atmospheric science, astronomy. It's all enabled by having a human infrastructure on the Antarctic continent. And I think if you imagine setting up a moon village or a moon base on that kind of model, it would similarly enable an awful lot of lunar science or planetary science that otherwise might not happen. Okay, I'll finish there. Thank you very much.
Okay, so we've got time for some questions. One at the back here. We'll wait till the microphone gets to you.
I have a loud voice.
Oh, okay.
You glossed very quickly over the theory of the origin of the moon. Would you like to fill in a few cases?
So, yes, well, it would be a talk in itself, right? I mean, pre-Apollo, the theories for the origin of the moon were that the early Earth might have been spinning so fast that you could have a circumterrestrial debris disk that had been shot out around, spun off the Earth, and you'd accrete the moon from that. That was George Darwin's idea. It's problematic because then you have to account why would the early Earth have been rotating? I mean, the Earth would have had to have something like a 2-hour day to be rotating fast enough to be shedding stuff off the equator. And actually there's also a problem. The total angular momentum in the Earth-Moon system doesn't add up. So, bit of a quandary, and there were other theories, right? But I suppose that rotational fission concept was arguably the leading contender prior to Apollo. What Apollo told us was that actually the moon is not made of stuff just spun off the Earth's equator, because it's lacking in volatiles and its mineralogy is different. So enter the idea that if you want some other way to form a debris disk around the early Earth from which the moon can accrete, but which isn't derived directly from the Earth due to the Earth spinning very fast. So a giant impact does this for you, right? So you're free to hypothesize at this point, right? So this point is a hypothesis. You're free to hypothesize what will happen if the early Earth gets hit by a giant impactor. Well, you'll end up with a debris disk around the Earth from which you can make the moon. And you can end up one without having to worry about the angular momentum in the Earth-Moon system, because you've introduced the angular momentum from outside. You don't have to worry about why the early Earth might have been rotating so quickly, because it wasn't. And crucially, when the Apollo samples come back, you can explain why it is that the lunar rocks, or the lunar mantle, is so depleted in volatiles relative to the Earth's, or certainly the Earth's upper crust, Earth's crust and upper mantle, because the volatiles will naturally be lost in this impact scenario. So that is the basis for the giant impact theory. But it's a hot topic, this, in lunar science at the moment. So I don't want to tell you that the lunar science community is completely wedded to this giant impact theory, but it's our leading theory at the moment for those reasons. It's a way of providing a circumterrestrial debris disk without having to have the Earth spinning too fast and still be able to not worry about the total angular momentum in the Earth-Moon system and the relative volatile poorness of lunar materials.
Given the considerable cost differential between robotic and human missions to the moon, how much of your program can be done robotically as opposed to requiring human intervention?
So there are several layers to this question. I mean, the short answer is, of course, some of it can be. You can imagine exploring the moon by sending 100 different sample return space missions to collect samples from 100 different places, and that will give you some sense of the diversity of the lunar crust, and you could do that without sending people, but you would have to send a lot of these missions. So, for example, if sending people to the moon, or ultimately to Mars, costs, say, 1,000 times more than a robotic mission, the question, actually there's a lot more to this than just science, but if we just consider it in a very crude science question, the question will be, would you get 1,000 times more science back by sending people than by sending 1,000 robots, each of which cost only 1,000 as much? And I think the answer to that is yes, you will get a lot more with people, because you will add capabilities at the upper end of the scale of technical difficulty. Right? If you want to drill, a current deepest Apollo drill core was 3 meters. The good reasons for wanting to drill into the moon perhaps to 100 meters or several hundred meters. There are reasons for wanting to drill into the crust of Mars of many kilometers to look for life that might be present in subsurface aquifers. Then you're at the kind of scale of exploration activity that having humans on the ground and all the stuff that they can bring with them probably will be enabling in a way that you're just not going to do robotically. So I'm not sure whether this answers. It seems that superficially it's a very simple question like this, isn't it? But as you look into the different layers of exploration, what you're trying to get out of exploration and what you can do, the relative speed of things, then I think Apollo did demonstrate that once they were there, they achieved much more than would be achieved robotically. I have written this up, but it's in another article. Perhaps I should send you the link.
Yeah, Apollo, of course, was 40-some years ago, whereas with the development of artificial intelligence and robotics, that may change the...
So it may do, but to my mind, it's not so much in the fact that the robots need to be very intelligent. It's the fact that they need to be big and capable. I mean, you could imagine miniaturizing an intelligent robot, so it could be highly intelligent, the size of my glasses case or something, but all the pressure robotically is to make missions small, because if they're small, they're cheap to launch, and if you can make them intelligent and small, then they can make their own decisions on the surface. But planetary surfaces are very big and complicated things. Little rovers the size of a shoebox. Doesn't matter how intelligent it is, it's not going to make any significant headway exploring a planetary surface if it just gets stuck behind boulders that are 10 times bigger than it is all the time. So intelligence is, it's obviously going to be useful. In terms of human-robotic partnerships, the more independent or the more autonomous rovers can be made, then the better tools they will be. But I don't think they're going to be a panacea for exploring planetary surfaces. The test will be whether we start using them just to explore the Earth, right? We don't explore Antarctica by parachuting robots into Antarctica currently, and the robots may get more intelligent, but I don't think they're going to get to a point where you say, oh, we'll just replace McMurdo as a research station because we've got these super intelligent shoebox-sized robots. I think it will be found that they won't be as capable as humans until they get as intelligent and as versatile as humans, and then the social implications of that, far transcend space exploration, right? I mean, once we're all uploaded into shoeboxes, then, space exploration may proceed along those lines, but then so society on Earth will also be so altered, be in a completely different ballpark.
Is it known what is causing the moon to move away from the Earth at 4 seconds?
Oh yeah, sorry, I interrupted you.
Well, as opposed to move towards the Earth.
Oh yes, that is the tidal interaction that was talked about earlier. So now the exact speed is interesting. This 3.7 centimetres per year. That does depend on the rate at which the Earth is slowing down, the day is getting longer, which is depends on the rate at which the tide's friction is dissipated within the interior of the Earth. So the rate, why it's exactly 3.7 rather than 3 point something else, or 2 points, it will have changed. Through geological time it will have changed as the distribution of continents has changed on the Earth. But why it's moving away rather than towards, yes. It's because the moon is located beyond the co-rotation, beyond geostationary orbit, essentially. If the moon was orbiting closer to the Earth than geostationary orbit, which is whatever it is, 32,000 kilometres away, then the moon would be coming towards the Earth, as Phobos is to Mars. So in about 50 million years, Phobos will impact on Mars, because Phobos, the tidal interaction between Mars and Phobos is causing Phobos' orbit to decay. But in our case, the moon has always been outside the co-rotation radius, and the tidal forces are driving it away, causing the Earth's rotation to slow down and the day to get longer. So the physics of that, yes, that is well understood.
Anyone?
In the giant impact scenario, presumably all the oceans on the surface of the Earth would have evaporated into space.
Yes.
Do we know where the current ocean water in the surface of the Earth comes from then?
So, I mean, this is a very interesting, and this actually, so there are several aspects to this, but some of it is relevant to a question that was asked this morning about whether the moon has rendered the Earth a habitable place. This giant impact, yes, it would have had a severe detrimental effect on the surface environment of the Earth at that time, and we would have lost much of the water if there were oceans on the Earth, and if there was a thick atmosphere on the Earth, we will have lost them. Now that actually, at first sight, seems a terrible thing, but actually if you think about it, if the early Earth had had 10 times more volatiles than it currently does, and it hadn't been blasted away by the giant impact, we might be sweltering under a runaway greenhouse now. We might be a Venus-like planet because the early Earth might have had too much CO2. So in this, you can speculate that the giant impact actually, despite being terribly detrimental at the time, might in the long term have rendered the Earth more habitable as a consequence. So we might, this really is speculation, right? But then it does follow that most of those volatiles that the Earth now has have come after the giant impact. And so there are only two sources. There's outgassing from the mantle. I mean, this impact was still very early on, right? So we lost a bit of mantle to go into what made the moon. But much of the Earth's mantle would have remained, and it would still have inherited volatiles from its own accretion, from icy bodies elsewhere in the solar system, and then outgas. And then, of course, the Earth's surface has been bombarded by water-rich bodies from outside. Subsequently, say, both comets and hydrated asteroids both will have introduced water. So our current volatile budget has come from the outer solar system, and it's either come directly through comets and asteroids bombarding the surface post-impact, or it came before the impact from comets and asteroids that were incorporated into the Earth when the Earth accreted and then subsequently outgassed. So either way, the volatiles have come from the outer solar system. It's just some of them have been through the Earth first and some haven't.
Okay, last question at the back.
In that photos with the chart you made of the cratering of the Earth's surface,
Oh yes.
initially it increased rapidly,
Right, well, so that's a question as to, so it is called the late heavy bombardment. The fact that there was this seemingly high flux of meteorites striking the lunar surface prior to about 3.8 billion years ago, this is referred to the heavy bombardment. So then you've got a question: where have all these asteroidal impactors come from? Now, of course, in principle, some of them could have come within the context of the giant impact theory. Some of them could have come from the circumterrestrial debris disk that we could try and make the moon out of. But it's clear, I think, that most of them didn't, because if you look at other surfaces in the solar system, like Mercury or the southern hemisphere of Mars, they have similar crater and basin densities as the moon does. So this kind of implies that the whole inner solar system was being bombarded by meteorites or comets. And the current prevailing theory for this is the orbital evolution of the giant planets, Jupiter and Saturn, can, or hypothetically did, stir up the asteroid belt at about this time, leading to many more asteroidal objects being sent into the inner solar system on orbits that crossed those of the terrestrial planets. So I think when we look at the heavy bombardment, it isn't something unique to the Earth-Moon system, because we see evidence for it elsewhere.
Well, why did it stop then at the 3 million, whatever point?
Oh, so you've got two reasons. Firstly, once all the impactors on Earth planetary crossing orbits have run into planets or been put onto orbits that don't intersect planets, then you've kind of used up your budget of impactors. But the other thing is, in this, it's called the Nice model, after colleagues in Nice who really sort of developed the theory. The Nice model relies on particular orbital resonances between Jupiter and Saturn and the asteroid belt. And these as the orbits, the giant planets moved, well, they've got quite a complicated theory. Giant planets initially migrate in, then they migrate out. They go through a time when they're very efficient at scattering planetesimals from the asteroid belt into the inner solar system, but then as their orbits move outwards again, this ceases to be effective. So I think there are reasonable explanations as to why the heavy bombardment stopped when it did, which was about 3.5 to 3.8 billion years ago.
Okay, we better move on. So thank you very much.